Richard Price, your host, and also the founder and CEO of academia.edu. So yeah, I get really excited to dig deep into academic ideas. But remember, I'm here to present and explore papers neutrally with you as my co-investigator. I'm not endorsing the arguments or taking a side here. I just love sharing what's out there in the huge world of academic research and seeing what insights we can take for ourselves. Today, we're diving into a paper by Dr. Trajan Terek, who, by the way, is a neuroradiologist and an independent researcher, also the author of something called the Fractalon Unified Theory. And fun fact, ChatGPT, yes, OpenAI's language model, is credited as a computational physics co-author on this one. How wild is that? AI as a co-author. Maybe I should try that for my next meeting notes. Anyway, the paper's title is Reflected Light Interpretation of the Double Slit Experiment within the Fractalon Unified Theory. Pretty hefty, right? Let's unpack what's actually going on. So you might remember the double slit experiment from high school physics, the one where light shines through two tiny slits and creates that classic pattern of light and dark stripes on a screen. This experiment is, well, legendary for showing us the weirdness of wave-particle duality in quantum physics. Light doesn't just act like a wave and a particle, it sort of acts like both at the same time, which is, let's just say it's always made my brain hurt a bit. But Dr. Terek's paper presents a totally fresh perspective. Instead of the interference and diffraction story most of us have heard, he says, actually, maybe those patterns are a geometric outcome of multiple light reflections that happen in this sort of structured, lattice-like ether that surrounds all matter. Why is this significant? Well, for one, if light patterns come from reflection in an underlying structure, not interference, that would upend how we interpret a central experiment in physics. That would mean maybe there's more order and geometry hidden in what looks like randomness. Some folks love that idea, others, not so much. Okay, let's talk about the methods and findings. Dr. Terek didn't just speculate, he ran actual experiments. He set up two thin cylindrical mirrors, think metal wires, parallel to each other with a tiny gap, and shone red and green lasers right through them onto a screen a couple meters away. He then took super close-up photos using an iPhone, which is just, something I'd love to see on Instagram. Honestly, here's the crux. The reflection model predicts distinct spacing for reflection bands depending on the wavelength. So red light with a longer wavelength should give wider spaced bands, and green with a shorter wavelength should produce bands that are closer together. And when Dr. Terek measured the patterns, he found about 120 stripes per millimeter for red light and 150 for green, exactly the proportionality you'd expect if wavelength was the controlling factor, not quantum interference, but geometric reflection. The theory behind this involves, and wow, this is a mouthful, the Fractalon Unified Theory. Imagine the vacuum as being filled with a cubic lattice of rotating units called fractalons. Light, in this picture, bumps into this structure and reflects off virtual mirrors that are defined by the arrangement of these fractalons. The equations in the paper show how the observed reflection angles and spacing directly tie back to the lattice's geometry, and the paper goes even further, connecting these reflection patterns to gravitational effects and atomic structures all through the same ether lattice. That's a big claim, and important to mention, this kind of approach, bringing back an ether idea after it was thought to be ruled out by, for example, the Michelson-Morley experiment, is very unorthodox in mainstream physics random thought here. I sometimes wonder if, like every field, has its own ether. Something we once thought was fundamental, then tossed away, but that occasionally tries sneaking back into new theories. Maybe the next scientific revolution will bring back something else we thought was dead and buried. Okay, anyway, let's bring it all together. What does this mean for you? Well, as a listener, whether you're into physics or just curious about the big mysteries of nature, this paper reminds us that science is ongoing. Even experiments from 2 centuries ago aren't set in stone. They're open to fresh interpretations, alternative explanations, and yes, occasional controversy. You don't have to accept every claim, but you can use these ideas to keep your own critical thinking alive. And again, just to be clear, I'm not here to declare this the truth. I'm presenting Dr. Terek's work for exploration and reflection, not as gospel. That's true for all research. Papers aren't pronouncements from on high, they are invitations to think and ask more questions. So thanks for joining me on In Depth with Academia. Remember, your curiosity is more important than having all the answers. Keep questioning, keep listening, and who knows, maybe you'll be next to shake up how we see the universe. Until next time, stay curious.